Okay, in this video, we're going to discuss Cohen's d for two-sample t-tests, a primary measure of effect size. Okay, so what is an effect size? Well, first of all, let's distinguish between an effect size and a p-value, and what's the difference between the two of them. Now, the p-value is the probability that a test statistic, for example, t obtained or the t-ratio, could be obtained as a result of sampling error. And obviously we'd like this to be small, right? So the smaller the p-value, the less likely that the result that we obtained was due to chance or sampling error. And if it's not due to chance or sampling error, then it's probably due to something else, like the true effect of manipulating the independent variable. Now, when the p-value is smaller than alpha, we reject the null hypothesis. Okay, so that's what a p-value is. So what does it really tell us? What does it communicate? Well, if you think about it, it's really a communication about the reliability of a result. It's really communicating the likelihood that chance factors, sampling error, can account for the test statistic. And obviously, we don't want that to be the case. We don't want sampling error to be responsible for the test statistic. So it's a measure of reliability, and it's not really a measure of the magnitude of an effect or the degree to which manipulation of the independent variable accounts for changes in scores on the dependent variable. So we need a new statistic that communicates better the magnitude of a treatment effect or the effect of manipulating the independent variable. So that takes us to effect sizes. They provide some index of the effect that changing the level of the independent variable had on scores on the dependent variable. And there's really, at this point with two-sample t-tests, there's really two main options for effect size. One is called Cohen's d, and the other one is called eta squared. Both express the size of the observed effect, but in different ways. And in this video, we're only going to look at Cohen's d. And the reason for that is that in the JASP software that I use with my class, and which is commonly used as people learn statistics, eta square is not included in JASP for two-sample t-tests. So Cohen's d is there, so it's a good idea to learn that. Although I will have another video on eta squared coming shortly. So for t-tests, JASP reports Cohen's d, but not eta squared. Now, you can think of the effect size as being expressed in standard deviation units. Okay, so Cohen's d, you'll see in just a moment, the denominator in the calculation is in standard deviation units. So that means that the statistic itself will be in standard deviation units. And when we say treatment effect, that simply means the effect of manipulating the independent variable or whatever it is that we're looking at in the statistic that we chose, in this case the t-ratio. The effect size will be expressed in standard deviation units. Now, we usually only do this if the null hypothesis has already been rejected. Okay, so here's our formula, and this is, technically speaking, this would be called estimated Cohen's d for an independent group's t-test because we don't know the population variance. We have to estimate that. So if that's the case, we're also estimating the effect size in the population, and we can build confidence intervals around that effect size, and you'll see that shortly. But here's the formula. We're just going to take the difference between the means for group 1 and group 2 and then divide by the estimated standard deviation in the population. Okay, so let's go over the example that was in a prior video of how to do this. If you recall, in that study that we were talking about, there were two levels to the independent variable. There was a video training in the use of distress words to communicate one's feelings versus, say, anger words. And we'd like to see an increase in those distress words after the training. And then there was a second group that had no video training at all, and that was our control group. Now, then there was a 5-minute discussion that each participant had with their partner, and the number of distress words were counted, and there was a difference in the means between the two groups in terms of the number of distress words that were used. So the first group that had the video training showed more distress words used in that 5-minute conversation than did the control group. So that's the first thing we need. we need the means for group 1 and group 2. And then the other thing we need is the estimated standard deviation in the population. Now, we get that we're going to start with the pooled variance, the estimated pooled variance. Okay, so we're pooling the variance together, and we already did that in the prior video, and that came out to a value of 11.31. Now, the estimated population variance is really the square of the standard deviation. So once we have the estimated population variance, then we just need to take the square root of that value, and we're going to get the estimated population standard deviation. So we take the square root of 11.31, and that's going to be 3.36. Okay, so now we have what we need to actually do the computation of Cohen's d. So here's our formula again. We just plug in our means in the numerator, so 14.14 minus 8.14, and then we have 3.63 in the denominator. Okay, and again, this is the estimated pooled standard deviation in the population, because we combined the variance estimates to get this, and then took the square root. And then 6 divided by 3.36, that's going to yield a value of 1.79. And so you might be saying, okay, so it's 1.79. What does that mean? Well, it's good to sort of take a look visually at what this means, because it helps clear things up quite a bit. Okay, so what we could do is we could plot out the distribution of scores for individuals not taking the video training, in other words, group 2. And on the horizontal axis, we will have the estimated pooled standard deviations for the population. Now, the center point of this distribution will be 0, and that corresponds to a mean of 8.14. And then as we move out to the right and the left, we go up by 1 estimated standard deviation, 2 estimated standard deviations, and so forth. Okay? But this is the distribution of scores for individuals who did not take the video training. And then what we're going to do is we're going to overlay on top of that the distribution for folks who did take the video training. So what we're going to do is we're going to locate where Cohen's d shows up in the first distribution. And that's going to be the center point of our second distribution. So with an effect size of 1.79, which of course corresponds to a mean for the first group of 14.14, 1.79 for Cohen's d would show up somewhere about here. Okay, and this difference between the effect size estimate of 1.79 and 0, right, really represents the size of the effect. We know also that when we look into a z-table, because these are in standard deviation units, so why not use a z-table? We know that the proportion of area under the curve of that first group's distribution that's above 1.79 is only 0.0367 if we look this up in a z-table. That means, we just subtract that from 1, that means that below that point would be 0.9633. So that allows us to make a statement that will be correct. The mean score for individuals in the video training was at the 96.33 or 96.33 third percentile of scores for individuals who did not receive the video training. In other words, the mean for the folks who were trained was way, way up there, way out toward the tail of the distribution of folks who did not take the video training. And that really sort of helps us visualize how significant the training was. Okay, now when we look it up in JASP, here's the printout that you're going to get, okay? Now you see over here, obviously, we've got our t ratio, our degrees of freedom, our p-values, and then as you move to the right, you finally see Cohen's d. So Cohen's d shows up, and fortunately, our calculations were right because it comes out just about to what we calculated. Any difference is simply rounding error. And so there's our Cohen's d. And then to the right of that, what you see is something that says 95% CI for Cohen's d. Okay, so this is a really valuable little statistic. It's the confidence interval. Okay, now keep in mind when we calculate Cohen's d of 1.784, that's based only on sample data. And so we know that that's not going to be exactly right in terms of the population, because as we know, there's going to be sampling error, in all the statistics that we compute. But by producing the confidence interval, what we do is we present a range of values within which we are 95% confident that the true Cohen's d in the population resides. So we're 95% confident that the true population Cohen's d is between 0.496 and 3.022. We just happen to observe in the sample a Cohen's d of 1.784. Okay, and that's pretty much it for the output. Everything is there, and the JASP output corresponded to what we did by hand, which is always a good lesson to note that if you ever want to check your work, go in and run it in JASP and see what comes up. Now, you might want to say, well, how do we classify these effect sizes? Well, Cohen in 1988 actually produced some guidance in terms of that, and what Cohen said was, look, any effect size from 0 to 0.2 we'd classify as a small effect. From 0.2 to 0.8 we'd classify as a medium effect, and over 0.8 we'd say as a large effect. Now, these are general guidelines, and you have to be a little bit careful because really the importance of an effect depends on the field and the research question, the history of research within a field. It could be that an effect of 0.10, which would be classified by Cohen as very small, could be a hugely important finding and a hugely important effect. If that corresponded to, say, a new drug for cancer that saved ultimately 3,000 lives, even though the effect size statistically in terms of the calculation is small, it would have a huge effect on other people's lives. So you have to be a little bit careful about how you classify these things. Cohen's table is really meant for guidance. There are also alternative effect sizes that are similar to Cohen's d. Cohen's d uses the pooled standard deviation. You saw that in the calculations. And that's okay as long as the variance for our two groups are equal. In other words, the homogeneity of variance assumption is met. But it may not be appropriate if the standard deviations are very different for the two groups. So there are alternatives provided in JASP. For example, there's Glass's delta. And what Glass's delta does is it's pretty much like Cohen's d, but it only uses the control group's standard deviation, just one of the variances there, rather than creating an estimate of the standard deviation that comes from the pooled variance. Okay, now typically in JASP, that would be the standard deviation associated with the second group that's entered in when running the analysis. There's also Hedges G, which is included in JASP, and that's a slightly different computation that might yield more accurate results, especially with small sample sizes. But for the most part, most courses will just focus on Cohen's d. Now, you might ask, well, okay, that's great for an independent groups t-test. How about the correlated groups t-test? Okay, well, let's try that. As you know, we had an example of a correlated groups t-test earlier in another video. And in that particular experiment, we were examining whether a new drug that was meant to improve short-term memory would increase the number of words recalled from a word list after 2 weeks of taking the medication. Now, if you recall, the mean D score, right, that was calculated was negative 3.86. And we also calculated, good news, we also calculated the estimated standard deviation of the D scores. And those are really the two things that we need in order to compute Cohen's d. So let's do that. So our estimated D in the population, which, by the way, no stats programs will call it estimated D. It's just going to be referred to as Cohen's d, will be the mean of the D scores over the estimated standard deviation of the D scores. So that's negative 3.86 over 1.95. If you have any question about where these numbers came from, just make sure to go back through the original video that presented this example. I'm just taking those values from what was already calculated. And then that's going to end up being negative 1.98. Okay, so here's how it will look visually for our correlated groups t-test and Cohen's d. We're going to start with the distribution of the post-test scores on the immediate recall test. So this would be our second sample that we're looking at. And the horizontal axis here is, again, in the estimated population standard deviation units. And we're going to overlay then the distribution for the pretest scores, and then the difference between those thick vertical black lines represents the Cohen's d that we calculated in estimated standard deviation units. So if you recall, our value is negative 1.98. So we're locating on this distribution the value that is negative 1.98 standard deviations away. And this then represents where the pretest group is, sample, relative to the post-test sample within the same individuals. Okay, so we have the pre here, and then the gray is our post. And you can see that there's a big difference, right? Because at post-test, well, at pre-test, the scores were much lower than at post-test. And that's why we had a Cohen's d of negative 1.98. Okay, so that's what the effect size means. That the pretest group, the scores of the pretest sample of the same individuals was negative 1.98 standard deviations below what was found at post-test. Okay, we can also then look at the amount of area above the pretest, right? And so that proportion of area is 0.9761, and then below it is 0.0239. So that allows us to make the following statement. The mean of scores on the recall task was 1.98 standard deviations below the mean of scores at post-test. The average score in the pretest condition was at the 2.39th percentile of the distribution for the post-test condition. This is a large effect size. That would be a correct statement to make. Okay, and then in JASP we have this kind of output. Okay, again, what we're going to see is the t-ratio reported here. And the fact that it has a negative sign is because we subtracted the scores from the post-test from the scores from the pretest to create the d scores. Here's our p-value. That's our measure of the reliability of the finding. In other words, how likely it is that this t-ratio that we observed could be explained due to sampling error, and that probability is very small. It's only 2 in 1,000. Okay, and we like to see that because that led us to reject the null hypothesis. Then we come over here and we see Cohen's d, which is at negative 1.976, round up it's negative 1.98. So again, it's confirming the math that we did. And then there's the 95% confidence interval for Cohen's d. And again, what that tells us is that in the population, we're 95% confident that the true population level Cohen's d is from negative 3.272 to negative 0.637. Okay, and then we write it up in APA format. And again, here's our general form that we'll use for all t-tests. And with the actual numbers that we obtained from our example, it would be T6 equals negative 5.23. That's our t-ratio, or obtained t-value. The probability, because JASP gives us an exact value, we might as well report that. So rather than saying p is less than 0.05, we'll say p equals 0.002, and then Cohen's d is 1.98. Now you'll notice here that I dropped the sign. I didn't say negative 1.98. Now, the reason for that is there's some folks like to report the sign for Cohen's d, and other people just report the value without the sign, the absolute value. And the reason for that is that it's really hard to conceptualize what's meant by a negative effect, right? Effects tend to be changes, and changes are always something that you should be able to observe, and a negative effect size doesn't make a lot of sense. So, so a lot of times you'll see folks that, because of the way the math is done, will get a negative sign, but in their manuscripts they just report the actual effect size in terms of the absolute value without the negative sign, which is what I did here. So results showed that scores on the immediate recall task were statistically significantly lower at pretest compared to post-test. And there's our APA notation. And again, if there was any doubt that the pretest was lower, this sign right here clears that right up, right? Because it's negative. So we don't really need to repeat that with the effect size sign. The effect size was classified as large given Cohen's classification table, Cohen 1988. Okay, big picture. P-values communicate the likelihood that a test statistic was obtained due to sampling error. So it's a measure of reliability, whereas effect sizes tell us the magnitude of a difference between two groups, or really just the magnitude of an effect. Cohen's D is expressed in standard deviation units, and how that standard deviation is calculated depends on the type of statistic we use to begin with. And the value of Cohen's D represents where the mean of one group is located relative to the mean of another group in standard deviation units. It doesn't have to be a control group, especially if you're doing a correlated groups design, but I think you understand what I mean there. And Cohen created a table that permits researchers to classify the magnitude of effect sizes. So that's Cohen's D. The other major form of effect size that can be used with two-sample t-tests is eta squared, and I'll have another video to talk about that.